Gritty Gabe has been vigorously training for his upcoming Olympic race. Today he was being extra gritty as he wanted to run up Mount Everest for his morning run.
I used to walk, I'm a gritty man, no time to talk. Mountain high and valley low, I've been at them all since I was born.
Oh no, I hope I don't fall.
When suddenly he tripped on his toe and hit his knee on a stone.
Now it's alright, it's okay. The doctors are here to save the day. And we can trust to understand the pain you're feeling there, young man.
You're a runner whenever you're at fun and you're staying alive, keeping your stride, feeling me breaking and everybody shaking, but you're staying alive, keeping your stride. Ha, 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 staying alive, keeping your stride.
Well, Gabe, I don't know what to tell you. Looks like you tore your cartilage and fractured your patella. But don't worry, a simple knee replacement surgery will be an effective treatment for you.
Knee replacement? What could possibly replace these amazing legs? Tell it to me straight, doctor. Will I ever run again?
So here's the deal. You will be undergoing a knee replacement surgery that will last approximately 1 to 3 hours, where we cut a small section of your knee to expose your kneecap and get on with the replacement. My friend Nick over here, the biomedical engineer, will talk to you a little bit more about the implant options you may have.
I propose that we should use a Chromium Cobalt knee implant as it'll allow this man to run again.
Chromium, cobalt, alloys, corrosion, what are all these terms?
What do you mean? Oh, will it be a success or will I be a straight mess?
What do you mean?
I've heard all the bad news, all the infection and news, but please help me.
Whoa, let's not get all scared now. So how about we run through some biomaterial basics so that we're all on the same page. You're going to be getting a chromium cobalt knee implant. But first things first, a successful biomaterial allows for its long-term usage in the body without rejection, and we analyze this by inspecting its mechanical and non-mechanical properties.
For example, hardness is a measure of the material's resistance to the indentation, and in your case, we would want the implant's hardness to equal your bone's hardness to prevent any abrasion from occurring.
We also look at the elastic modulus, which is characterized as the proportion of stress to strain inside a corresponding limit. And it demonstrates that a chosen biomaterial, in your case chromium cobalt, has comparable deformable properties with the material it's going to supplant, such as the area of your knee.
Fracture toughness is used to determine the longevity of a biomaterial, as it indicates a material's ability to resist failure. Therefore, a high fracture toughness is an indicator of clinical reliability.
We also look at fatigue life, which is the length that the material will last before reaching complete failure. Resistance, which focuses on the biomaterial's ability to tolerate a long-term wear and abrasion from the surrounding environment. And also its biocompatibility, which determines the material's ability to function in a living system without producing any adverse reactions when exposed to the actual body.
Okay, wow. Okay, it is way more reassuring to know that you guys have looked into all the aspects of the material that will be used for this implant. So, thank you.
Hold on a minute, son. Now, docs, tell me about chromium, cobalt. Why not choose gold or diamond? My son deserves the absolute best. After all,
he's a runner, he's a track star. He needs to run each day until he gets far. I can't take the pain if he gets scarred.
We were just about to dive into chromium cobalt. So cobalt-based alloys are highly resistant to wear and have amazing mechanical properties such as high resistance to fatigue and cracking. They're not brittle, they have high elastic modulus, high mechanical strength, and high biocompatibility. And because of all these characteristics, the cobalt-based alloys are well suited for applications under mechanical stress, especially those involving friction, such as hip and knee joint implants, such as what Gabe will be needing.
However, with a high modulus of elasticity, there is a higher chance for fractures or loosening of the implant to occur compared to other biomaterials. But with follow-up appointments with your surgeon, we can make sure your implant is working like it is supposed to.
Okay, everything sounds good. Except, I will be honest with you, I have heard some pretty shady things about chromium cobalt implants, how apparently, like, these metal ions can get inside of the body after joint movement. and it apparently causes these allergic reactions. So if you could elaborate on that, please.
Yeah, according to WebMD, when the metal is coated, the metal ions can escape through the pores or the cracks in the coating. It especially happens when the metal rubs on metal, like in this knee replacement. I've also read that this can potentially lead to cobalt poisoning, and we both know that's not good.
Yes, that's true, but only about 1 to 2% of people experience a negative effect when exposed to cobalt. And studies have shown that allergic reactions to cobalt are more likely to only affect older patients.
Well then, it's a good thing I'm young. But I've also heard that it's got a pretty crappy crystallinity structure. Wanna enlighten me on that, Doc?
Ah, yes, of course. Well, you probably heard of the close-packed hexagonal structure of chromium cobalt. However, with a simple temperature change of 421 degrees Celsius, it becomes a face-centered qubit, which, I'm sure as you know, is far less brittle. But if you are still skeptical about the implant, Nick will tell you all about our testing process.
Honestly, I would love to hear more about the testing process. It's not that I don't trust you guys, it's just I would like to, know what I'm getting myself into.
No need to fret, sir. In recent years, there have been new ways that chromium cobalt alloys have been tested on handling certain criteria like this. Actually, some of these tests and methods have been used to improve the capabilities of this alloy structure for applications such as knee implants.
That was too vague. I want the details, all of the details.
All right, then, let's talk about the different types of tests performed on chromium cobalt alloys. Let's talk about first selective laser melting testing, otherwise known as SLM. It's a new testing method that creates a three-dimensional metal application that are manufactured by a high powerful laser to melt together metallic powders as they layer upon designated material. This test is highly accurate and is capable of forming complicated pieces for specific parts of medical applications. We use this type of testing since it allows us to create chromium cobalt alloys that have more promising characteristics than normal traditional materials.
So next, we'll talk about CAD-CAM milling. This technique is used to mill or grind up restorations of frameworks from solid materials into solid components. This test is used to eliminate the flaws and the porosity of the material as it undergoes the machine working processes of the material. Testing using this technique was done also along with the SLM testing to compare the characteristics of the cobalt chromium alloy. And it was found that both testing methods resulted in the same bond strength, same yield, and tensile strength. So overall, both SLM and CAM milling are effective testing methods to test cobalt chromium properties.
Now, the past two experiments that we explained are typically used on dental implants. Now, why bring these testing methods up? Well, easy. Chromium cobalt can be applied to any implant type, so the data from the last experiment is essential to understand this alloy's properties. For this next experiment, alloys were tested on their wear properties on metal contact, such as a knee replacement. The test followed ASTM standards as the test utilized the spherical flat tip on the surface of these tested alloys. In the following table, we can see the loss of weight material after each cycle was done. As we can see, there is very little weight loss of chromium cobalt material upon contact with other materials.
The final test performed on chromium cobalt alloys is called SAMS, otherwise known as the self-assembled monolayers. This testing method is used to enhance the capabilities of chromium cobalt composites. SAMS testing is a testing method used to enhance the capabilities of chromium cobalt composites. Structures of SAMs are formed by spontaneous chemoabsorption of surface molecules. Not only does this test change the chemical properties of the surface of the material, but it also changes the material to the most desired condition. Overall, the use of SAM testing can provide more hardness, higher modulus of elasticity, a better strength properties of chromium cobalt alloys for specific applications.
Yeah, well, Google says there usually is more analysis, such as surface characterization and the chemical and mechanical analysis done.
Oh, we can definitely keep diving deeper. When we look at surface characterization, scanning probing microscopy will be used to characterize the surface of the deformed alloy at a nanoscale level. Scanning electron microscopy, otherwise known as SEM, is a type of microscopy that utilizes a focused beam that consists of high energy electrons in order to create a variety of signals at the surface of a specimen. It shows that we definitely analyze this material all the way to its atoms to ensure it's for good use.
When looking at the chemical analysis, chromium cobalt alloys are known to experience levels of oxidation when stable chromium oxide films are formed. But this rarely happens, so as long as you go to all your follow-ups, we can make sure that you will be all right.
And talking about mechanical analysis, the hardness of chromium cobalt alloy to have a hardness range from 499 megapascals to 1442.1 megapascals, depending on its weight percentage. The alloys have a tensile strength that ranges from 550 megapascals to 800 megapascals, but upon heat treatment, these values can radically increase, showing that your implant will be durable in the long run.
Well, I think you guys have convinced me well enough.
Despite my doubts, I learned from the amazing medical team that failure of chromium cobalt alloys in orthopedic implants have been analyzed using the mechanical properties regulations for creating a successful biomaterial. It checks off everything on the checklist, inspecting the hardness, elastic modulus, fracture toughness, fatigue life resistance, and biocompatibility. It was concluded that chromium cobalt alloys presented the exceptional mechanical properties which included high wear resistance, high mechanical testing, high corrosion resistance, and high biocompatibility, which are all ideal for a knee replacement or any other joint replacement. I also learned that the material is not perfect and that there's a chance of fatigue and stress concerning the mechanical failures, as well as fractures with high levels of activity, but with regular checkups, everything would be okay.
Yeah, you can go the distance, you can run the mile. Even with an implant, you will run with style. You've heard all the failures and you've heard the pros. Chromium cobalt does not fail like before. Doing good for people, learning as we go. Taking risks will get you farther than before. Do it for our country, do it for your name. Cause there's gonna be a day when you're
Gritty Gabe did end up getting the knee replacement, and he happily ran even when he was very old, as he had never faced any serious side effects from the chromium cobalt alloy implant.